Alright, so now let us look at one complete example of a circuit which is similar to our RC circuit if you recognize it. I have one switch, but I have two connectors here, point A and point B. Do you recognize that when I'm at point A, the battery is here, so the inductor is being charged, so-called, or we are in the storage phase. That means energy is being stored here. When I'm at position B, battery is already being removed from the circuit and the inductor is therefore releasing energy into the circuit, and that's called the decay phase, right? So we say when switch is at position A, we are in the storage phase. Alright? Okay, let's talk about the VL. What is the expression for VL? When I'm at position A, okay, remember we say he's a very stubborn person, he will resist current flow, so he will develop a voltage of 20 volts, right? So VL is 20 to 0 volt. So it's decreasing function. So it's therefore 20 E minus T over time constant. Correct? How about VR? Well, here is 20 to 0, here will be 0 to 20. Correct? So it's an increasing function, so it's 20, 1 minus E minus T over time constant. Okay? What is then the current expression? Current is VR divided by R, so it's 20, 1 minus E minus T over time constant divided by resistor. Voltage, ampere, right? And what's the time constant in the circuit? Time constant is L over R, so it's therefore equal to 6 milli divided by 5K, so it's 1.2 microsecond times 10 to the power minus 6 second. Alright, so we can I'm able to write out my expression for VL, VR, the current expression. I'm able to calculate the time constant, right? Then part E. How long would it take? For a steady state? It means to say finally the current is just 20 volt divided by 5K. Right? The answer is 5 time constant. So it's 5 times 1.2 microsecond, so it's 6 microsecond. Okay? Right, part F. At T is equal to 2 microsecond, at T is equal to 0.8 microsecond, find VL. Can you do that? Of course, substitute the time into the expression. VL is equal to 20 E minus T over time constant. So substitute 20 E minus 0.8 micro. Time constant is 1.2 micro. So I can get the answer. Right? Part G. Find what is the time when VL is equal to 14 volt. No problem. Substitute into the formula. VL is equal to 20 E minus T over time constant. So 14 equal to 20 E minus T over the time is 1.2 micro. So time is unknown. One equation, one unknown. Time can be found. Alright? Okay. So with that, let's draw a graph. If you are asked to draw VL graph when it's charging, okay, it's a decreasing function, so it decreases, right? And here's your 5 time constant, which is equal to 6 microsecond, okay, and it started with 20 volts, so that's the VL. And VR is an increasing function. Okay, and VR increased to 20 volts, right? And it takes 5 time constant to reach the steady state. Okay, and to draw the current waveform is also an increasing function, right? It's also 5 time constant, which is 6 microsecond. But what is the value of the current? The current is 20 over 5K ampere. Okay, so able to draw the graph? Shouldn't be too difficult, right? Okay, so with that now, we move on to say that the switch now is being thrown to position B. Alright, now it's thrown to position B. We are now not in storage phase anymore, we are in the decay phase. That means discharging. Alright, now the current was already flowing this way, and it was 20 divided by 5k ampere. Okay, so he has therefore act as a battery source now, and the battery source is going to be 20 volt to 0 volt. But the battery source must reverse the polarity, right? In order to provide the current to flow in the same direction. So my VL, which I want to define to be like that, so I must put it in negative sign. So VL is going to minus E minus D over time constant because it's decreasing. Okay, so that's VL. How about VR? VR is the same. Here's 20, here's 20, 19, here's 19. There's one voltage, one resistor. So VR is equal to E minus D over time constant. Current, VR over R, so it's also decreasing. Right? So if I were to draw the graph, okay, VL is a decreasing function, but it's a negative sign, so it's a waveform that is being flipped. So it's flipped like this. Okay, it's flipped like this. So here's the 5 time constant, right? And here's my minus 20 volts. So that's my VL. Right? And VR, if I were to draw my graph, is a decreasing function. So this is my VR, right? So again, here's 24, here's 5 time constant. And current is a decreasing function as well. Here's 5 time constant, and the current here is 24 divided by 5k ampere. Got it? So that is the complete picture of RL circuit. Okay, now I think we should therefore test it with our general function, because the general function, like what we did in the capacitor, also works for the capacitor. Okay, let's try. Alright, so let's talk about the current. Or even we talk about the resistor. So will be what? V infinity plus V0 plus minus V infinity E minus D over time constant. Right? Let's test out with one position will do. Alright, when I throw at position A. So the story goes like, it was initially 0 volt. When I throw my switch, he wants to resist the current, so he develops 20 volt, right? 20 volts to 0 volt. Okay? Alright, so let's talk. Finally, is 0. Initially, 20. Finally, 0. So with that, you actually come up with an expression that is without a bracket. And that's correct, right? Yes. Okay, let's talk about the current expression. Current expression is also equal to I infinity, I0 plus, plus minus I infinity E minus D over time constant. Okay, the I expression. Okay. What is the final current in this circuit? Finally, this becomes a piece of wire, right? So the final current is 20 volt divided by 5k. So 20 divided by 5k. That's the final current. What's my initial current? Initial current, there's no current, right? So it's 0. And minus final current is 20 over 5k, E minus D over time constant. So I have 20 over 5k, bracket 1 minus E minus D over time constant. So it's an increasing function. Look at it. So in order to use this expression correctly, you actually have to know the story. What is the final value and what is the initial value? Right? Okay. And if I were to test it with position B, right? So now let's test it with position B. Okay. Now the switch is thrown to position B. If it's thrown to position B, your VL, in order to maintain the current flow this way, it must develop with a 20 volt, right? So it's 20 to 0 volt again. But the polarity now is going to be like this. Still remember our negative sign? Yes. Okay, so let's try. Finally, it's 0. Initially, should be minus 20 volt, correct? Because I put my arrow this way. So it should be minus 20, minus 0, E minus T over time constant. So it's minus 20, E minus T over time constant voltage. Alright, let's test on this current to find the current. What is my current finally? Finally, the voltage will be, the energy will be used up, right? Finally, there should be no current in it, right? So it's 0. Initially, is the 20 volts divided by 5K. Finally, no current. So that is equal to 20 over 5K, E minus T over time constant. Get it? So I want to emphasize again, if you want to use this general expression to come up with the correct answers, you must know the story. If you do not know what is finally, what is initially, you will not get the correct answer. Okay, and that's why I started the lecture by telling you the story first. You must know the story before you can plug in the value. Alright? Now again, many students are asking, what is this 0 minus 0 plus and infinity? Now what it means is actually about a time axis. Right? Say when we talk about 0 minus, 0 plus and infinity, what it means is actually a time axis. This is my time axis, and here is 0 second. 0 minus means is the very short duration before it, so that is called 0 minus. And a short duration after it is called 0 plus. After a long time, that is called infinity. Infinity. Okay, so let's revise our capacitor. If I say here is 20 volt and this is VC, right? The switch is closed at 0 second. So initially it was no charge, it's 0 volt, and finally it's going to charge to 20 volt. So let me ask you, before the switch was closed, what was the voltage? It is 0 volt. After the switch was closed, shortly after, it is still 0 volt. Right? This takes time to charge, right? Yeah. Finally, it is 20 volt. Get it? So that's called a capacitors. Capacitors. So now let's talk about the inductor. Now it's inductor, right? Inductor. Okay. Inductor, let's talk about the current. Current spectra. The current in the circuit, 0 minus, current 0 plus, and current infinity. Now before the switch was closed, there's no current, right? Open circuit, so it's 0 ampere. After the switch is closed, remember we say it's a very stubborn one, he wants to maintain no change, he will develop a 20 volt to resist the current, so there's no current. Right? Finally, he surrendered. He cannot resist the current forever. So finally, the current is 20 volt divided by the resistance. Okay, so that's for the inductor. That's for the inductor. Now, this is about the current. Okay, let's talk about the voltage then. VL. Before the switch was closed, it was an open circuit. VL is equal to 0 volt. But once the switch is closed, he's a very stubborn person, he wants to resist current, so the voltage he induced immediately becomes 20 volt. Right? And finally, he cannot surrender, he cannot sustain it forever, the 20 volt will be reduced to 0 volt, right? So finally this becomes 0 volt again. That's the meaning of 0 minus, 0 plus, and infinity. So you must know the story or the characteristic of the circuit in order to be able to understand the meaning of 0 minus, 0 plus, and infinity. Okay? Alright, cut.